Okay. So, okay, everything is okay. So, perfect. First, let me note that I removed one link from the list. What you see now, it's an updated list of links. We are currently at the Earth system. So, this part which I'm talking about now is not in the PowerPoint. So let's focus here on the web page. And I would like to discuss with you how to derive and write the Reynolds theorem, Reynolds transport theorem, which is the basis for deriving conservation equations. Basically, the Reynolds transport theorem is a theorem that establishes the principle of conservation with respect to a control volume where a given matter, can be mass, can be energy, is transported into the control volume by the movement of a fluid that is passing through the control volume. And this is, for instance, for the mass associated to water, is flowing in and out from the control volume by following the flow of water through the surface of the control volume. Like in the tank, the rainfall enters into the tank through the surface that is delimiting the control volume. And there is also the possibility that we have a source term into the control volume, which can be also the gradation term. And the Reynolds transport theorem also allows for the movement of matter in and out from the control volume, matter that is not associated to the movement of fluid, like for convection, for instance. There is a movement of heat through the control surface, through the surface of the control volume, without necessarily a flow of a fluid that moves through the surface. So the theorem establishes the general principle of conservation equation. You have to expect that given that the change in storage is accounted for, you have to expect that it's expressed the theorem in differential form. And then from the theorem, like plugging into the equation resulting from the theorem, plugging in the matter that you are interested in, like energy, mass, we derive the individual conservation equations. I think it's a useful information to know what are the equations that we can use to build a climate model or an Earth system model in general. I think it is useful to know the theory behind these equations. Actually, the Reynolds transport theorem, if you look on the web and you look for a formulation, it's a bit complicated, and it is expressed in vectorial form, and I mean, it's a bit complicated, especially in terms of notation. So there are available on the web several simplified forms. I am proposing here a mix. It's a form that is simplified with respect to the general framework. You will see how it is simplified. On the other hand, it is not very simplified. Actually, I tell you that I tried to elaborate my personal interpretation in order to obtain something that can be easily understood by, at the same time, preserving the conceptual structure of the theorem and the general framework. I think it is correct, but to tell you the truth, I'm still a bit doubtful because I couldn't find in any reference on the web an expression of the Reynolds transport theorem as you find here. So if you are interested in knowing more and you have some suggestions to give, you are much welcome. I trust it is correct. So this is our control volume, okay? And it's a generic surface with the volume V, and the surface delimiting the volume is called S. And here you have infinitesimal surface ds. I need to refer to infinitesimal surfaces because, as I said, the process is not homogeneous. And therefore, I mean, the velocity, for instance, of the flow through the surface is varying depending on where I move with my ds. So there could be a part of the surface that is not subjected to flow through, like in the tank. There is only the bottom discharge, the bottom hole, where I get some flow out, and there is only the surface of the storage where I get some rainfall in. The walls of the tank, I have no flow through the surface unless there are some leakages, okay? And therefore, I mean, I have to account for these differences, and therefore I need to refer to an infinitesimal surface ds. The volume is by itself infinitesimal because, I mean, let's say, no, not necessarily. The volume can be also extended, but we have to take into account, this is what I meant to say, that if we extend the volume, we lose the possibility of describing the variables inside the volume. So we can extend it, but as I said earlier, if we extend it, we have to be fully aware that we get an average estimate of the variables of interest through the volume. Another thing, the normal vector is for each surface ds, we need to define the normal vector. It is a unit vector. I think this is implicitly assumed here. And now we check, but maybe that I add it and I specify it's a unit vector. I think it is, I mean, it is usual practice that when we get the normal vector is a unit vector, but just keep it into account because I think it's not for now specifically explicited here that it's a unit vector. Okay, and look, the vector is pointing outward, okay? Normal vector to a small portion, so I should write here normal unit vector, okay? Okay, so let's consider an arbitrary property. Here is called capital phi, and it's expressed in units of the property itself. So if it is mass, it's kilograms. If it's energy, is the unit of energy, and etc. And in the volume V, so the property, as we said, can be energy, mass, heat, or whatever. And lowercase phi is the density of capital phi in a small portion, the V of the volume V, okay? And density means like mass density, so mass per unit volume. So the unit, if the property capital phi is mass, the unit of capital phi is kilograms, and the unit of lowercase phi is kilograms per unit per cubic meter, okay? Perfect. And okay, and then the quantity capital P within the volume can change for three reasons: a source term, okay, or flux of phi through the boundary. The flux through the boundary can be split in two components, as I said. It's flux associated to fluid transport, or in absence of fluid transport, for instance, for conduction. So the change over time, basically, this is the equation from which we start. The change over time of capital phi inside the volume can be expressed through this relationship. So we have a change in time of the integral of mass density over the volume. Okay, so we assume here that mass density can vary inside the volume. If not, we can just remove the integral and say a change in time of mass density times volume, okay? And this is expressed, so this first term on the left-hand side is the correspondence of dWt over dt in the linear reservoir, okay? It's a change in storage, okay? Perfect. Now, let's look at these components. Let's start from the last one at the right-hand side, because it's the simplest one. It's the integral of the volume V of the source term expressed in matter per unit volume. So it can be, for instance, mass density, okay? And let me see if it is specified because I want to review it. The source term, okay, I forgot per unit time. The source term is expressed in unit of capital V per unit time and unit volume, okay? And then you see that it's dimensionally equivalent to the left-hand side, okay? Perfect. Now, what is the middle term? The middle term is the transport of matter through the surface associated to fluid movement. You see the velocity term here. But here, it's expressed in scalar forms, which means that lowercase v is the component of velocity of transport along n. Okay, so it's basically, in other formulations that are expressed in vectorial form, it is written as a vectorial product. Just explain over the blackboard, and it's just a formula, so they don't turn the camera. So we have this things, okay, this is my S. And we have the normal vector, okay, this is the normal vector. And let me put the sign of vector bottom, and this is the unit, don't forget, okay. And then we have a vector v of velocity coming out, okay. If I want to compute the flux through this of the matter lowercase v associated to the movement of fluid with the velocity given by the vector v, this is given by v external, scalar product, okay. And this is equivalent if we can indicate it as v v, where v is the component of the velocity vector v along the normal end. Okay, so this allows me to avoid the vectorial formulation in this start. Okay, not sure if it is a simplification. I used it. F dash is the same thing, but F is the component along n again. Okay, so F in general is a vector, and when it is indicated as a vector, I put the overbar. Later on, I am forced to refer to the vectorial form. You will see, and I put the overbar. Without the overbar, F is the component along n of flux of P in absence of fluid transport. And this is expressed in terms of P per unit time and unit surface. Okay, so basically, yeah, this is very simple, actually. Left-hand side, change in the storage with respect to time. Right-hand side, flux per unit time through S not associated to fluid transport, flux associated to fluid transport, and source term, which can be a degradation term. Here you have the minus sign because the vector is outward. Okay. Perfect. Now, of course, these three components not necessarily have to be present altogether. The source term can be limited. But like, for instance, usually when we apply mass balance, we don't have a source term. We have an external flux, like in the linear reservoir, but there is no source term. But sometimes there could be a source term, even for water, for instance, because you have a source, okay? A spring inside the catchment. If you have springs, this is water that comes into the catchment without being associated to the current rainfall. It's associated to maybe very previous rainfall, okay? And the same for convection. Could be there, could not be there. But in general, we need to write in general write it by considering these three terms. So basically, this is a formulation in a simplified form of the Reynolds transport theorem. Okay? In a simplified form because we don't see vectors, so it's expressed in scalar form. And but on the other hand, if you click on this link here, this is a Wikipedia page that is quite, quite complicated. This is a general form that is in vectorial form, but you can recognize basically it. I don't think here there is, let me see. I don't think there is the, yeah, okay. It's basically the same. There is no source term here, okay? And because probably it's included in one of these two terms implicitly. And then you see that, you know, there is the proof. We don't have the proof, but basically I provided the proof by giving a conceptual explanation. So it's clear that these are what are the fluxes that we have considered. But if one wants, it can be mathematically proved. Yeah?
That product is internal or external?
I don't think I understand the question. What is internal product and external product? Sorry for
the
that.
output of internal product is the scalar.
No, it's a scalar.
So in the mathematics, we use dot. Not
okay.
I'm very important.
No, not. It's not. It's not. And maybe that later on I use later. I use the term scalar product, and I think I was use the term scalar product for internal product and vectorial product. Yeah, I think so. I'm not really sure if maybe I am outdated. Okay, let's forget about this. Now, let's try to put it in a form that is more directly applicable, because in this form, I mean, we need at least to compute the integral. So here there is the example of the linear reservoir, which we already discussed. And now let's, this form can be applied in both continuous fields and non-continuum fields. But if we refer to continuum mechanics, which is what we are interested in, now we have to assume that the field of the property capital Phi is continuous. Again, the previous formulation applies even if the field is not continuous. In continuum mechanics, usually we assume that this is continuous, like for instance in classical fluid mechanics, okay? So if we are interested in describing the spatial and temporal variability of the system, V must be small, okay? We already discussed it. Okay, now, let's now call into play the Gauss theorem, which allows us to replace the surface integral with the volume integral. So we can use this relationship here. And here, sorry, I needed to put a capital S here. And so I can substitute this two terms that previously were at the right-hand side with a unique term that is the divergence. Now I have to pass to vectorial form of f plus lowercase v divergence, which is integrated over the volume V. So divergence, what is divergence? Divergence, as you may remember, is derivative of, in this case, capital F with respect to x plus derivative, etc., etc. Now, why here I needed, sorry, partial derivative, yes, yes. And here, why I needed to go back to the vectorial form, because I am integrating over V, and over V, the vectors, the vector F and V are not necessarily aligned with the surface and don't have the same direction that the normal at the surface. And therefore, if I want to make an integral, I have to account for them in vectorial form here. And in fact, I write where capital F over bar and the lowercase v over bar indicate vectors depending on spatial coordinates. So they depend on the three coordinates inside the volume. Now, because we are in an inertial frame, the time derivative, and this is an independent relationship of the integral, is equal to the integral of the local time derivative, and therefore I can make this substitution. Okay, and this is independent. 4 is independent by 3, but we can plug 4 and 3 into the first equation, which now we can express in this way. And this is the V. Now I'm taking note of all the questions and I'm correcting. Okay, this is a DV, a capital V, not the lowercase. Okay, and this is just by plugging in. Now, given that capital V is of arbitrary shape and size, now it can be satisfied, this conditions here, only if the term in square brackets is 0 everywhere, and therefore we get this relationship, which is the general form of the conservation laws in continuum mechanics. And then you can assume, like it's usually done in continuum mechanics, but not always, you can assume that capital F is 0, meaning that the only fluxes through the surface are those that are associated to movement of fluid. If capital F is 0, of course, here you obtain something more simplified, and then you are ready to plug in the quantity instead of lowercase p, the quantity that you wish, like mass and whatever, and you obtain from this equation the conservation of mass, the conservation of energy, and you can recognize basically that also the linear reservoir can be derived from this equation, okay? And of course, the linear reservoir then needs to be integrated like this equation. It's in differential form, needs to be integrated in order to get an explicit representation for the matter of interest. This is the Reynolds transport theorem. What should you know about this theorem for the exam? Not everything that is depicted here. This is a mathematical proof that is, I will not ask at your exam. And you should remember the assumptions, and if you can write the start, this equation is fine enough. Okay, equation 1, sorry. It's fine enough, okay? But it's the most important thing is that you are able to explain the assumptions and the components of this equation, okay? So the change in storage over time is given by blah, 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 blah. 3 terms, and you can describe them. Okay, this has been a bit technical, but I think It is one of the few technical things that I ask you to in a way to start. Okay.
But maybe the application is for payments here.
Yes. No, this is from. It is the start. It is the Rails theory.
Okay. So getting the start then for the Gauss.
Yeah, but you don't remember to. You don't need to remember the Gauss theorem. Okay. And what I can ask at the exam is, for instance, something related to the linear reservoir. This may be asked. I need to check. Yeah, but it is there. You saw it. It is also in the web pages. So coming back to your question, I discussed it in the room. It's in the web page, the linear reservoir, and therefore I could ask it. Okay. So, I hope this helps in understanding. Of course, going back to your question, the question was, should I study everything that is displayed in these web pages for the exam? No, not everything, because as I said, I am only asking what I discussed during the lectures. And maybe that if you demonstrate that you know some more, this is a plus for you. But for instance, don't make. I had a student once, who basically the first question was really great, and he went well beyond what I explained in the lecture. And then second and third question, he didn't know anything, and he said, "Okay, but I studied well the first question." Yeah, but it is the only thing that you know. Okay. Sorry? Yeah. Yeah, it's here. It's here. Okay. And of course, there is not the entire development, but it is there. And I may also ask some more of what is depicted here, because it's clearly, it's here. Okay, and I think it is also somewhere else, but anyway, this is enough. And of course, try not to be very rigid, meaning that by just recalling this example, today for the linear reservoir, I did something more. So don't assume that I can only ask the equation in integral form, the equation in differential form. I could also ask to make some subsequent development. For instance, here, in this equation, you don't see PDT minus QDT. You see only the general expression. You see it here, but under the assumption that there is, let me check. Yeah, under the assumption that there is no change in storage. So there was an intermediate step here, which I drew over the blackboard, and is not here. Sometimes when the few proofs that I make, sometimes when they are transferred to the lectures, they are simplified. Some steps are not reported here. And don't assume that because they are not here, these steps which I explained during the lecture cannot be asked. I mean, these are general suggestions, but you know that when you study, you have to integrate. In general, just follow the advice that what you believe it is useful, try to study it, and what you believe can be easily remembered. Usually I try not to ask questions like the full development of the conservation equations, because it's, I mean, it is something that it's a memory exercise, and I'm not interested in that. Okay, good. Uncertainty, we already talked about it, and we will talk about it later. So let's forget about it. And now let's get into, just 1 second, I just want to, okay, perfect. Let's get into more details in the specific form of the Earth system models, and in particular, the climate models. Here there is a discussion of natural disturbances, but this discussion is very educational. There is nothing particularly scientific, and read it, don't skip it. And these are interesting because these are it's a list of forcings that sometimes we neglect into the models, but actually some of these forcing may occur. Like for instance, an earthquake is a source of energy because earthquake is a potential energy that is released in the form of kinetic energy. And usually when we make models, we don't make models of earthquakes. I mean, we make models, a statistical model of earthquakes, but when we model the Earth system, we don't include these perturbations, which may occur, for instance, for volcano eruption. It's another release of energy that was stored in terms of potential energy inside the Earth and then is suddenly released outside. These are usually not considered, but like asteroid impact is absolutely not considered. This is an exception to the closeness of the Earth system. But on the other hand, don't assume that they can always be neglected. There are some cases where we need to consider them. Okay. Sorry. The cooling of the Earth's nucleus is yeah. It's do you know what it is? Yeah. It's in the Earth system models usually it's not considered. No, no, because it is okay. It is a very slow process, but usually it's not considered. And geomagnetic reversal, it's another thing that is not considered. You may know that it happened in the past, and it may happen also in the future. And it will not cause human extinction, but still, it's something that is still unknown. I mean, I'm saying that it will not cause human extinctions because the scientists are quite, they proved that in the past, when it occurred, this didn't cause a big disruption of the ecosystems chain, and therefore we assume that it's something that will be disturbing, but not causing human extinction. But still, it is, you see, there have been at least 183 reversals. Yeah.
So this natural disturbance we just know that not present, but
in the models, we don't consider them usually. Okay, but in some of the cases, you may consider it. Today, there is, for instance, an increasing attention to compound risks, multi-risks. So people are starting thinking what may happen if during a flood there is an earthquake. And it is something that is not impossible. And you may say, okay, but it is very unlikely. True. But on the other hand, there is an increasing attention to events with very low probability and very high exposure. Yeah, and therefore, clearly, it's a matter of concern, and so there is an increasing attention on that. Compound risks, some of them have a relation, and like for instance, in the industrial risk, an earthquake can be associated to the explosion of some industrial plants. Or like it occurred in Japan, a tsunami was associated to, the tsunami caused the problem with the nuclear power plant of, I don't remember the name, it was Fukushima, yeah. And so there is an increasing attention to these compound risks, and so, but for the geomagnetic reversal, you see that on average there has been one every 450,000 years, and the latest was more than, no, about twice that time ago. So it's not so unlikely that it happens. Okay. Now, more details, as I said, about these models, and then we can turn to the next lecture. Climate models. Okay. So what you see here is a figure of a grid covering the globe. And I think, let me see if there is an higher resolution. A grid covering the globe. And this is a hypothesis of decomposition of the Earth into elementary volumes. And this figure is displays that it's not only the surface that is gridded, but also the depth into the Earth, which is explored through layers. So indeed, they are elementary volumes. First, a consideration. The higher the resolution, of course, and the higher the level of detail. So with the progress of time, we evolved from so-called coarse resolutions, and a coarse resolution is a resolution, for instance, of the grid over the land surface of 50 kilometers, so 50 by 50, which means 250,000 square kilometers, square kilometers. And now we are moving to final resolution. The last generation of models works at about when the domain is large, like Europe. The final resolutions today are about 3 by 3 kilometers. And at the urban level, where you can limit the area that is modeled, you can also go down to 1 by 1 kilometers. So the resolution is an essential component of an essential feature of the global model, of the climate model, that gives to you an idea of the reliability. Second consideration, you may have noticed that I am using two terms to define a model, a climate model. I use the term climate model and the term Earth system model. Actually, these two terms are not synonyms. The Earth system models are considered to be the last generation of climate models. And why this change of name? Because, as the new name suggests, people realized, scientists realized, that it's not just enough to describe, to include in a model among the unknowns or state variables. It's not just enough to include climatic variables. People realized that variables which are more typically land variables, like vegetation cover, evapotranspiration. Evapotranspiration is the sum of evaporation plus transpiration, and therefore depends on the vegetation cover. River flow, groundwater flow are, in a way, essential components of climate. And therefore, the idea was, given the increase availability of superpowers, computational powers, supercomputers, that give the possibility of running very demanding tasks, the idea has been that of increasing the complexity of models by creating models that reproduce everything. So if you get the latest generation of CMIP6 models, which you can download from the Copernicus data store, for instance, or from the other sources that Ray will tell you, these models also simulate runoff production. They don't simulate directly river flow, but they simulate runoff production. And if you aggregate, you integrate the runoff production over an area, for instance, a river basin, you get an estimate of the river flow in some of the cases with very interesting results. So the results are quite reliable in some of the cases. Why I say in some of the cases? Because, as you can understand, the reliability of these models is spatially varying. There are some, and not only spatially varying, there are some variables that are well simulated, and there are some places that are well simulated. And on the other hand, there are some variables that are not as well simulated, and other places which are not as well simulated. How can we recognize these changes in reliability? First, you have to consider the variable and ask yourself whether the variable is highly heterogeneous, if it is non-linear, if it is non-Gaussian. Non-Gaussianity and non-linearity, you know what non-Gaussian means because you know what is a Gaussian distribution. Non-Gaussianity and non-linearity are related to each other. Usually when a variable is non-linear, it's also non-Gaussian. And how can you recognize linearity? It's very simple. Take a variable like temperature and ask yourself whether with a linear regression or a piecewise linear regression, you can represent it fairly well, piecewise with long pieces, okay? If the answer is yes, it means that the variable is slowly varying, is varying with a very regular pattern, it's close to linear. Temperature is close to linear. And in fact, if you try to see the probability distribution, you draw a probability density of temperature, it's close to Gaussian. Daily data of temperature are close to Gaussian. If you look at rainfall, first it's intermittent, and therefore it's not linear. Okay? If a variable is intermittent, it's not linear, because you can't approximate with a straight line something that is intermittent. Rainfall is spatially varying a lot. And if you try to fit it with a straight line, you don't succeed. You need, I mean, if you try with a piecewise linear regression, you need a lot of pieces, okay? So if a variable is highly nonlinear and highly non-Gaussian, you should elaborate the idea that it's difficult to simulate it. It's difficult to reproduce it. There is a lot of uncertainty. This is the first consideration. Second consideration, look at in terms of geographical location. You can understand when a land is simple and when it is complicated. Think of the roof of an house. It's very simple. I mean, it's very simple to model it, to model the exchange of heat, to model rainfall runoff. It's a very simple structure, and you clearly recognize it. So the same for the land. Look at a catchment that is very flat, okay, very flat, and a catchment that is very steep. It's clear that where it is steep and very spatially varying with a lot of variability in up and downs, it's more complicated. And look at a region, for instance, for which you want to model climate, and look at the morphology, like many mountains, more complicated, and like exposure to several different forces, like the storms usually come from the same direction. It's less complicated. Or cyclones. If it is an area that is subjected to cyclones, it's more complicated because cyclones means a lot of turbulence. So first of all, you have to look at the process and elaborate your idea, like, okay, this is simple or not? And if it is simple, you, of course, may have an understanding that uncertainty is more reduced. Okay, so second, let's discuss how these models are structured. And we already know that they are based on conservation equation. And here there is a discussion about the spheres, and it's already given in the previous lecture, so we skip it. And also here there is some recall of tipping points. In here there is a reference to water, and let's forget it. It's not really important. Okay, I'm not interested in these numbers also at the exam. And why this example is provided here, in order to emphasize the complexity and non-homogeneity of the Earth system in terms, for instance, of water cycle. Here there is an example of turbulence and explains that indeed this is something that is affected by a lot of uncertainty. And let's jump to the structure of the models. So, and let me just see and take, okay, here it is. But let me take the PowerPoint, sorry. Because otherwise it's, if I go through the lecture, it becomes more distracting. You see, here there is what I basically depicted before. Here there is written black box because it's a figure that I found over the web, but keep in mind that when we say black box, usually we mean empirical models. Black because it's not, I mean, it's not clear. It's something that you can't see inside. Physical model is more transparent. And let's now skip the history of climate models because we will discuss it later. And just go here. Okay. Let's go back to this figure. So, first, depending on what you want to simulate, you have to identify the equations that need to be applied in any grid cell. Okay, so if for the case of the linear reservoir, we have two equations, that's fine. And these equations depend on the initial condition. The solution of the equation depends on the linear initial condition. What is the initial condition for the linear reservoir? It's the initial storage. I implicitly assumed that the initial storage was 0. Okay, and given that the linear reservoir is only one control volume, I have only one initial condition. Okay, and what are the boundary conditions for a linear reservoir? The boundary conditions are, there are actually, let me think, for the linear reservoir, I don't think we need to specify any boundary condition because a boundary condition would be, I think it's the input variable, rainfall over time, that can be considered a boundary condition because yeah, it describes the inflow through the boundary and therefore is a boundary condition. And this is a very simple case, but in general, if you want, for instance, in Earth system models, simulate many variables, you have more equations. So you first identify the equations that you want to apply. Conservation of mass, conservation of energy or momentum, depending on the level of detail that you want to reach. And there might be conservation of heat if you want to describe the temperature. So you identify the equations, and here becomes the problem. These equations have to be applied at any given cell. And the problem is that for any given elementary volume, you have to give initial and boundary conditions. And actually, as you may have already understood, boundary conditions means also the flux of the matter through each contour. And this flux depends on the solution of the neighboring cell. Okay, so basically, when you solve these equations, you have to solve them at the same time for all the grid cells. And of course, the influence of the boundary condition is reflected only on the neighboring cells, but still any cell has a neighbor, so the solution has to be done all together. And the number of cells for a climate model depends on the resolution, but very easily is like something 30 millions which means that if you have 10 equations for each cell, you have something like 300 millions of equations which need to be solved altogether. And now you understand why we need supercomputers, and you understand why we need why only a few research centers in the world can run these global climate models. These models run every day, and usually they give available every 6 hours the simulations to be used for the regional models. Because, as I said earlier, if I want to go down to the resolution of 3 kilometers, this is not possible at the global level. Or it is possible, but it takes something like years to generate. And therefore, normally what we do is at the global level, we generate with the resolution of 25 kilometers, and then we get the results and downscale at the regional level with what is called a regional climate model. Everything is written here. Okay, what I'm saying, you find everything in, okay, boxes have variable dimension with increasing computational demand for decreasing box size, what I said. Models have box size projected over the land varying from 100 square kilometers, so 10 by 10, for detailed models to detailed, actually 10 by 10, but I said that recently, but very recently. So for instance, simulation of 3 kilometer resolution for Italy, they are produced during these years after the pandemics, thanks to the funds of the National Recovery Fund. They increase the resolution. Candidate equation, we talked about it. So basically, let me just focus again on the few research centers. They make the data available. I think Ray explained to you where the data can be found, or probably not, because no, he explained to you where you can download the simulations. Yes, yes. So he explained to you where the data can be found, and then this data serve to run the regional models. Just to give you an idea, I said that in Italy, the simulations for the whole Italy has been produced only recently. This simulation at 3 kilometer resolution are particularly important because at this resolution, at this fine resolution, we can simulate convective processes. Convective processes are particularly important because they generate the summer storms. Okay. Do you know the difference between convective rainfall and so-called frontal rainfall? Frontal rainfall is the big perturbation that lasts for maybe 1 week. Very easy to predict because we know in advance. Like we know when a cyclone is arriving, and the frontal rainfall usually generates a rainfall of low intensity, but which lasts for a long time. Again, they are the big perturbations. Okay, and these usually cause problems when they are extremes for large rivers. And you know why? Because we said large rivers, they are put in critical condition by rainfall lasting for a long time. In this frontal rainfall, there is no or limited, very limited convective processes. So during this perturbation, it's very rare that you listen to thunderbolts, the sound of thunderbolts. Okay? Usually you are very surprised when you are like in November, like now, and you get some thunderstorms. It's really unusual, okay? Because it is not convective. What does it mean, convective? Convective is a rainfall that is caused by the convective rays of humid air that gets with a high concentration of humidity. Okay, so air that is very humid and it's very humid because the temperature usually is large, and therefore there is a high retention capacity of the air to absorb water in vapor form. And then this water that is very warm goes up and then gets to cooler conditions, condensation and thunderstorms. And this is the convective process, which usually is very local. It's difficult to predict. And by the way, is what seems to be more sensitive to global warming. I mentioned to you that we noticed that large-scale floods seems not to have increased in the past 30 years. Convective storms, and therefore floods from convective storms, have increased a lot. And this is why we realize that it is needed that we go to find a solution with these models, because we have to reproduce convective processes. But these simulations, which are produced by this model at 3 kilometer resolution, they can be produced only for max length of 30 years. And therefore, typically, now they are producing the simulation for 2070, 2100, 30 years. And so it's a bit of a problem because from these simulations, we need to estimate the extremes, but with 30 years only, it's a bit of a problem. And so you can understand what is the computational demand for a domain that is as large as Italy, which is not so large. You can simulate. It takes 1 year of simulations running on supercomputers. And then you get only 30 years. Of course, maybe next year, you may say, yeah, okay, but 1 year for 30 years of simulation, with 3 years, I cover the full sample. Yeah, but next year, conditions are already changed because you have more information, you have a model that is changed, so you have to start back. So the evolution is so quick that you can't really, the model that was running 3 years ago is already obsolete. And therefore, you understand the complexity. And also, you understand why the advent of supercomputers, you may remember Leonardo and the supercomputers by ECMWF in Bologna. So in Bologna, we have two of the, I think Leonardo was, when it was inaugurated, it was the most powerful computer at the global level. And now I think it's the second, I think something like that. Leonardo was inaugurated like, in Wikipedia there is written everything. Leonardo was inaugurated like a couple of years ago. And so you understand that it is extremely complex. And another implication is, but you already know that the data are really massive, huge, really huge. And to manage this data, it's not easy. So even you need a computer, a personal computer that is quite powerful. And you already experienced that because only to download the data is a bit of a problem. And the other thing is that if you want to manage this data, actually you need to work with a powerful code, which means not very user-friendly, okay? Because you have learned how to work with Python or R. Actually, Python for this big data is more powerful than R. But this requires you to get acquainted with programming and coding. It will become, I think, in the future, probably more accessible. But I think that this has been a kind of a step that clarifies how it's important for an engineer today to be also very good in coding. It was also like that 30 years ago. And then there was an explosion of user-friendly platform, which in a way decreased the need for engineers to be expert in coding because there were commercial softwares that were made available for almost everything. But now I think that this recent development of big data, artificial intelligence, now gave another push on the need for expert programmers. So there is indeed an increase of requests for engineers that are very good in programming.
Seeing the results that we take the average. While when we, for 1 year, we take 30 years, from this rate, with treatment in 3 years, we can cover those and when we get the average. As it's true that the data will be constant, but if we get the average of what we get,
I mean, you mean average over time or over space? Over time, yeah, but you know, the problem is that the average over time is, of course, it doesn't give you, for instance, an idea of extremes. So if you want to estimate extremes, you need 100 years of data. The problem is that I say 100 years, but actually it should be even more. So the problem is that to generate these 100 years of data, I understand what you mean. You could say, okay, I get in 3 years the simulation, which is 3 years old, but I can still use it. Yes, this is what also people do. So, for instance, now we are using climate models for estimating the extremes by using the models that were available in 2020. But what we noticed is that they are not good. And therefore, people increase the resolution and now they are at 3 kilometers. And now, but the results that we can get now are still not sufficient. So maybe that in 2 years from now, we realize that the resolution of 3 kilometers with this model is fine. Actually, I think that in 3 years from now, there will be another model, which I'm not really sure, but which may require more computational efforts. I think there is a limit because already now we reached to a level where I don't think we can really increase the computational resources in terms of efficiency. I think we may increase in number of supercomputers, numbers of a size of the supercomputer, but I think there is anyway a limit. You may have heard that there is today a great concern for the environmental impact of these supercomputers because they are really boiling up the rivers because they need a lot of water and then they to cool down the computers, and they are releasing the hot water in the rivers, and there have been recently a couple of publications and investigating the environmental impact, and a couple because they started 1 year ago to work on them. I expect many more environmental impact. So I'm not really sure whether we can really get to a digital twin of the Earth system that is high fidelity. I'm not really sure. And some of my colleagues say yes, for sure, because we will refine the resolution and we will find a way of running maybe only one at the global level of these models. And I'm not really sure because still, I mean, the improvement is clear. If we look at the testing that has been done on these 3 kilometers resolution models, the testing is very satisfactory. But still, okay. Here there are a lot of things which are very, I mean, descriptive. I don't want to discuss all of them. I think it is interesting that you get a look because it is a very easy read. There are some details on which I want here. Let me just check one thing. Okay, I wanted to talk about emission scenarios. First, I'm not sure I am fully updated because I think that probably the acronyms have changed after the release of CMIP6. But anyway, the acronym may have been changed, but the essence is not changed. And what is the essence? The essence is that an input, a fundamental input of climate models is the CO2 concentration. Okay? And the CO2 concentration for the future, which it's not an easy task to estimate, because we already discussed that describing the carbon cycle is not easy. There are several uncertainties. But there is also the component of the unpredictability of human actions and the evolution of human society. Think of, for instance, the carbon emissions are tightly related to demographics. And it's, it's difficult to predict what will be the evolution of human population in the future. So basically, the only solution is to make several different assumptions, like let's suppose that everything goes really bad, and we get what is called RCP, was called RCP 8.5. As you see, the acronym RCP has been introduced in 2013. But I think that with the release of AR6, Assessment Report 6 of the IPCC, I think they introduced a different classification, which I think is called SSP or something like that. Anyway, let's refer to RCPs, which is still, and you can easily look on Wikipedia what is the last set of emission scenarios. And they change continuously, and this is why they change continuously because they continuously update the models, the social models predicting the future emission. And they change continuously, and this is why they also change the way to call them. And in any case, what is common is that they make different assumptions. So one assumption is the future will be very bad. And another limiting assumption is the future will be perfect. We'll get to a fully decarbonized society by 2050. And therefore, the result is that we have several different emission scenarios. And you have to be careful about what you select. Let me see if there is, here is a description of the scenarios from RCP 1.9. And this is a pathway that would meet the goal of the Paris Agreement of 2015, which is a very ambitious goal, and it's basically already clear that probably won't be achieved. And then the last one is RCP 8.5. Let me see if I have a figure. And no, I don't have a figure, but somewhere there is a figure. Let me check. Okay, perfect. Very good. Let me see. I think I have something here.
Yeah, and the slide of Professor Logo.
Okay.
Yeah.
No, this is projection of global warming. Oh. Okay, here it is. And this is in terms of the RCP. And this, I think I introduced it last year, maybe. But it is CMIP 5. So I think in CMIP 6, they have changed the scenarios. But here you can see a clear picture. And you see that there is, you can distinguish between them, not only in terms of the final concentration, but also in terms of timing to the cap. So basically, you see that almost all the scenarios, all of them, reach a cap of CO2 concentration. And we think that we are reaching a cap for many reasons, but also for the mitigation policies. And you see that the most optimistic ones predicted that a cap will be reached between 2020 and 2030. Indeed, there are some researchers, very few of them, that demonstrated that we are very close to the cap, but very few researchers. I mean, I could find a paper that demonstrated that indeed by 2030, probably if we are not in the cap, we will be very close. By analyzing the progress of emissions, it is not true, like some media say, that there was no effect in the CO2 concentration. We already observed a decline in CO2 concentration, which it is probably due to the mitigation policies. You can never say that because, you know, CO2 concentration could have been mitigated by several other factors. But I mean, it is very likely that it's also related to mitigation policies. And therefore, depending on the scenario that you select, you have different, of course, results. So the basic question is, what scenario should we choose? I discussed it also with several colleagues recently because they keep using the most pessimistic one. Actually, the European Union tends to say to use the most pessimistic one. Still, at the European level, there are indications that are not so firm. They are a bit. Sometimes they also suggest the RCP 4.6, and so basically. There is to say that why this discussion? Because the problem is that RCP 8.5, it is delivering results that are very, very conservative. And you get changes in climate that may prevent any mitigation policy because they are so huge, these predicted changes. They look unrealistic, first of all. So, for instance, increase of temperature, they predict like 4 more degrees up to 2100, which is unlikely. It is really unlikely, based on the progress that we are observing now. And so the problem is that when you make a cost-benefit analysis of a mitigation policy, the cost becomes very large if you take these scenarios. And therefore, from several scientific opinions, we get the suggestion to refer to RCP 4.5 and not 8.5. Actually, if you look at the model outputs that you can download now, sometimes you see strange things like the output from RCP 4.5 that is more conservative with respect to the output of RCP 8.5, especially at the local level. If you look at, if you average over a large domain, it's fine, because what we expect is that change is lower for 4.5. So if you average over a large domain, this is fine. I made some experiments at the local level, and at the local level, you really see a lot of uncertainty. And you really see this contradiction, which is something that, and I didn't look at the last generation of models at 3 kilometers. But still, I spoke with one of my colleagues in Padua, and he's working on these models, generating now, and he said, still. And so you see that, anyway, it's an important selection. My advice, try to look at both of them and see what's the difference. And I think indeed RCP 8.5 is a bit too much. It's very heavy. I think this is anomaly. Negative means, let me see, gigatons. Yeah, but I think this is maybe anomaly because it's gigatons of CO2, and I'm not sure whether this is an anomaly, which is possible. Maybe that they refer to the difference with respect to a baseline, and the baseline, I need to check this emission, and I think there is. Yeah. Yeah, you are right. It is. I didn't think of it, and the solution is to look at the reference, and there is this figure is taken from there, and there is the reference, and solid lines are CMIP6. Yeah, this was only recently included, but indeed it's the CMIP6. I think. I think it is taken by the report of CMIP6. CMIP6 is coupled model intercomparison project 6, version 6. And we should look at it. I have a look. Yeah, it's a good comment. You see that there is here a reference, I notice it now, several discussion on the likelihood of RCP 8.5. Likelihood means reliability of RCP 8.5. And here there is a reference in 2020 and two references. There has been a lot of discussion on that. Okay.
Continue to do global warming.
Yes.
So below 1 degrees. When we talk about concentration, I think we are needing a temperature.
Because the concentration of CO2 has a direct effect in the temperature, as the model suggests. And as I mentioned maybe the first lecture, and I mentioned that the current models cannot reproduce the warming that has been observed without including the human emissions.
Okay.
So the CO2 concentration has a direct effect.
So the RCP will consider only CO2 concentration or other kind?
No, only CO2.
Only CO2.
And CO2 is not the only one greenhouse gas, but this scenario of future emission refers to CO2. If you ask me if climate models also take into account the concentration of methane, for instance, I would say not, but I'm not really sure. I'm not really sure. One should look at the description for models. Okay, and there is to say that there is a reason why CO2 is given priority, and because it is the greenhouse gas that is most affected by the anthropogenic activities. Methane is important, but is not so affected. There is a lot of methane that is released by the oceans, for instance, but it's not directly related to anthropogenic activities. Okay, let me just show you a final slide. And see, there is the slide somewhere. Not here, not here. Okay, no problem. Okay, yes. Okay, a very simple example of a climate model. I mentioned to you that it's possible to consider the globe, the Earth system, as a unique control volume. And indeed, it is possible. And so if I consider the whole system as an homogeneous entity, I can impose the radiative equilibrium. And the equation is this one. So basically, S is the solar constant at the left-hand side, the incoming solar radiation per unit area, and you see the value there. A is the Earth average albedo, which is about 8.3. And the albedo influences the quantity of energy that is reflected back into the space. And then R is the radius of Earth, we know it. And sigma is the Stefan-Boltzmann constant. And I'm moving at the left-hand side. And it's a constant for which we know the value. And epsilon is the effective emissivity of Earth, and we know the value. The only unknown here is temperature at the power of 4. And therefore, we can get, based on the knowledge of the solar constant, the albedo, and the Stefan-Boltzmann constant, and the emissivity of Earth, we can get an explicit relationship for temperature. And indeed, if you solve it for the values that are given in the previous slide, you get an average Earth temperature of 15 degrees. Actually, the average temperature is 14. Yeah. So it is very precise. Of course, it is precise because I think that the Earth's emissivity and the albedo probably have been calibrated a little bit, which is fine. I mean, it's clear. But you can see this is being the first example of climate models. A climate model for temperature. It's only one equation. It's not in differential form because you don't need to compute here the change in storage. So it's an equilibrium. So equilibrium means that the storage doesn't change. And therefore, that's it. And it's very simple. And I think it is a nice example. Okay, I think we have almost completed. Now I want to check if I said everything. So maybe next week I get that a little bit to the stop, but I think you have almost completed here. And now you have the theory, the basis for understanding how the numbers that Ray proposed to those of you who are attending the lab were generated. Questions? Okay, thank you very much.